Specific heat of a gas. We are used to finding the specific heat of solids and liquids using the formula mc change in temperature as the heat supply. But this specific heat, the small c that we use, refers to amount of heat required to raise the temperature of 1 kilogram of the substance through 1 degree Celsius or 1 degree Kelvin, it's the same thing, and that is in SI units. So we are talking about per unit mass. But if I come to per unit mole, so we are talking about molar specific heat. Molar specific heat is the amount of heat required to raise 1 mole of the substance through 1 Kelvin. Supposing I supply a small amount of heat dQ and the temperature rises by a small amount dt, this is the amount of heat supplied per unit change in the temperature per mole. N is the number of moles. This is the definition of molar specific heat. But this quantity depends on the conditions under which we measure it. For example, let me draw our cylinder containing gas. So this is the airtight piston. And then we have, let's say, some sand on top of that as the weight. So the pressure is equal to the weight of the sand plus the weight of the piston divided by the cross-section area. That's the pressure of the gas when it is in equilibrium. Suppose now I supply heat to it at constant pressure. That means I don't change the amount of sand. So in other words, I'm calculating the molar specific heat at constant pressure. So I supply some amount of heat, and of course I have a thermometer which measures the temperature change. Constant pressure means I don't change the amount of sand. So as I supply heat, what will happen? The gas will heat up, it will expand and push against the sand, and it will do some work. Let's say I supply 35 joules of heat, and that means Q is 35 joules. And let's say the gas, by pushing up, does 25 joules of work. Then the change in the internal energy, remember, according to the first law of thermodynamics, is going to be 10 joules. And that 10 joules goes into raising the temperature which we measure. Now, supposing instead I supply the heat at constant volume. At constant volume. How do I do it at constant volume? As I supply heat, it tries to rise. So I keep adding sand to keep the volume fixed. So the pressure increases, but the volume remains constant. So volume, if it is constant, the work done by the gas is zero. I'll call it, during an infinitesimal process, the small amount of work done is zero when I supply an amount of heat dQ. Let's go back to large amounts of heat. Supposing I supply 35 joules of heat again, but this time the gas does no work. So all the heat goes into raising the internal energy. So dQ is equal to du. So we find that the internal energy has risen by 35 joules. So I expect the temperature change to be much higher in the case of constant volume process compared to constant pressure process. So what do I expect for C, the molar specific heat? This, not dQ infinitesimal. When I use 35 joules, it's delta Q, I will just call it Q, divided by change in temperature. Now, in the case of constant volume, the change in the temperature is much higher for the same heat. So CV will be much less than CP. So we expect CV to be less than CP. Let me repeat that part. In the case of constant volume, to raise the temperature by 1 Kelvin, supposing I need to supply 10 joules of heat for 1 mole. So CV will be 10 joules per mole per Kelvin. But in the case of constant pressure process, if I supply 10 joules of heat, I find that it has lost 3 joules of heat in work. Only 7 joules has gone into raising the temperature. So temperature doesn't go up by 1 Kelvin. So to raise it by 1 Kelvin, I have to increase the heat more than 10 joules. So the amount of heat supplied per mole per degree Kelvin, Cp, will be larger than Cv. So in the case of Cv, we have this relationship. Cv is equal to 1 over n dq by dt. We are calculating this under constant volume conditions. I get 1 over n du by dt. I want to now point out, for ideal gases alone, there is a wonderful theorem that says the internal energy of the gas depends only on the number of moles and the temperature. It doesn't depend on the pressure, it doesn't depend on the volume. If I keep the number of moles constant, which I am doing in most of these processes, and if I keep changing the temperature, internal energy will change. But if I keep the temperature constant, even if I change the volume and the pressure any way I like, the internal energy doesn't change. We don't prove this theorem in this course. You just have to take it for granted and keep in mind that this is true only for ideal gases. So, if I go to a constant pressure process or a constant volume process or some other process where the pressure and the volume are changing in some crazy fashion, there are infinite number of processes possible. For any of these processes, the change in the internal energy depends only on the change in the temperature. Which means, if I find how the internal energy changes with the temperature for one of these processes, it will apply to all processes. Because the difference between this process and other process is we are changing volume and pressure in different ways, and that doesn't affect the internal energy. For example, in the case of constant volume process, we found the change in the internal energy is NCV dt. If you go back to the previous page, you see du is equal to NCV dt. So this tells us you take a gas at constant volume, find out how much heat you supply to raise the temperature of 1 mole of the gas by 1 degree Kelvin, and that measurement that you make will give you CV, right? And in future, you can use this expression for change in internal energy for any other process. What's the difference with some other process? In some other process, for the same dt, same n, it will be the same du. Even though in other processes, pressure is changing different ways, the volume is changing in different ways, but the internal energy doesn't depend on pressure and volume. Supposing I measure CV in a constant volume process, I can use that in this expression and use this du for any process. So now, if you're doing any thermodynamics problems, you're going to remember that we are going to have these equations to play with. Very important for you to memorize this. We have first law of thermodynamics, minus dW is equal to du. For gases, dW is pdV, right? And we have PV is equal to nRT, is equation of state for an ideal gas. And we have change in the internal energy is NCV dt. Both of these equations valid for ideal gases only. The other two equations, this equation is valid for anything in the world, this equation is valid for any gas. Okay, so these equations you must commit to memory. Now let's go to remember now we have measured CV. So we know, let us say CV for oxygen, nitrogen, helium, methane, ammonia and so forth for various gases, and we have made a table. Kinetic theory of gases will help us predict these values. So before I come to that, let's look at a different process, CP. In the case of the gas in the cylinder, we don't change the amount of sand. So let's go back to right. Remember, I want to calculate CP. That means I want to calculate 1 over n dq by dt under constant pressure conditions. So let's start with, I need dq. Now watch how I do this. This is the same procedure that you'll be using when I ask you to calculate C for any process. So you have to calculate dq by dt 1 over n for that process. So we start with dq. dq of course is equal to du plus pdv. I have taken pdv that side. du, remember, we can now substitute ncv dt if we are talking about an ideal gas plus pdv. Alright, now take a look at this. I want 1 over n dq by dt. I have n and dt out here, I can bring it to that side. Unfortunately, this does not contain dt. or n? If there was, I can take 1 over n dq by dt and find out what it is. So I got to figure out how to get rid of this. Previously, we got rid of this for constant volume process by putting dV is 0. But now dV is not 0. Pressure is constant, which means dP is 0. So we use a trick. We use the product rule for derivatives. dFPV is PdV plus VdP. Derivative of P times V with respect to anything, maybe temperature, maybe something else, is going to be leave P as it is, differentiate V, then leave V as it is, differentiate P. This is the product rule for derivatives. Right? From this, we can substitute into this. So we get dq is equal to ncv dt plus pdv. Pdv can be written as what? dfpv minus vdp. Wonderful. Now I can put dp is 0. Got it? Okay, now what shall we do with dfpv? So I'm going to write this in yellow color out here. dfpv, I'm going to go to pv is equal to nRT and write dfpv is equal to n is constant, r is constant, nr dt. Lo and behold, we got n, r and dt. So this equation becomes n cv dt plus pdv is dfpv, which is nr dt. So we get 1 over n dq by dt evaluated at constant pressure is n dt. You take it to that side, I get 1 over n dq by dt. What do I get? Cv plus r. So we get this wonderful relationship Cp is equal to Cv plus r for ideal gases. Got it? Okay, let me give you a problem. Before I give you a problem, remember what is the procedure? The procedure is, in order to calculate specific heat for any process, remember you have to calculate 1 over n dq by dt. How do I do that? For dq, you start with the first law. It already has ncv dt, so there is an n dt. So you got to figure out some clever way of getting rid of pdv so that you have n dt on both terms and bring it to that side, and you will have specific heat for that process. Here is problem number 1 for you guys. There is a process described by PV to the power of 2 is equal to constant. We can call that constant K or C or whatever you like. Okay? Find the molar specific heat for this process. For your information, what does this look like on a PV graph? Pressure versus volume. So P is equal to constant divided by V squared. If it is constant by V, that would be an isothermal curve, which would look like that. On the other hand, our process is constant by V squared, which means it falls faster. So a graph might look something like that. So this is PV is equal to constant, and this is PV squared is equal to constant. It's good for you to learn what functions look like. Go on. Now, you don't need the graphs for this problem. Go ahead and try solving it. Okay, let's see how this works. Right? So we start with, as always, dq is equal to du, which is ncv dt. I'm assuming it's an ideal gas, plus pdv. So as always, there is an n dt here, and keep in mind we are trying to calculate C for this process, which means we are trying to calculate 1 over n amount of heat supplied per unit mole per unit change in the temperature. So we need to calculate this function for this process, right? So I have P and V derivatives. So let us differentiate both sides of this equation. If I differentiate, product rule, P times 2V dV, right? If I'm differentiating, let's say with respect to temperature, is going to be P times Derivative of V squared with respect to temperature is chain rule. First differentiate with respect to V multiplied by dV by dt. So I'm not specifying what I'm differentiating with respect to, so I can just write it like this. Plus, don't forget, product rule, leave V squared as it is, differentiate P. This is equal to derivative of constant is 0. So we have, from here, I can divide by V throughout. Volume is not 0, so I can divide by V. So I get 2P dV plus V dP is equal to 0. So I get P dV from this, I can substitute. Unfortunately, I end up with V dP. And dP is not 0 now, because pressure is not constant. So I still have this problem. I have not been able to solve it. So now I reach out for the other equation. PV is equal to NR. Once again, let's differentiate both sides. I have P dV plus V dP, that is the product rule, is equal to NR dt. Nice. So can I use these two equations to eliminate V dP? So from this equation, I am going to subtract this equation. 2 PdV minus PdV is PdV. VdP minus VdP is 0, is equal to minus NR dt. Wonderful. We have achieved what we want to achieve. So now we come here. I'm going to write in yellow now. dq is equal to NCV dt plus PdV, which is minus NR dt. So take N dt to that side. So I get 1 over N dq by dt, which gives me specific heat for this process. Molar specific heat is equal to CV minus R. Problem solved. Now you know what you need to do. Start with the first law and assume it's an ideal gas. For du, substitute NCV dt and figure out some way of getting rid of PdV by using the equation of the process, and PV is equal to nRT. Figure out how to do that. So get some practice in that. Try your own function. For example, maybe try P squared V cube or PV cube is equal to constant or something, or try straight line graph. Straight line graph might be this, which is P, y is equal to mx plus b. So P is equal to mv plus b. Find the specific molar specific heat for that process. Okay, I'll leave that as an exercise for you.